All right, this is section 11.5, and in 11.5, what you're going to see is that we're going to take the fundamental counting principle. You guys remember, multiply all your options in one by all your options in another and all the way down. We're also going to take our permutations. Recall that permutations are n factorial over n minus r factorial, NPR, and order mattered, right? In permutations, there was some kind of ranking, and so that was really important to take into account. And then finally, we're going to also see combinations, NCR, n factorial or n minus r factorial. Remember that, or recall that combinations order no matter on the order, right? And there was no ranking. Something to keep in mind when you guys are going through this is, remember the ice cream scenario. If you were getting ice cream, if you were looking to get a cone, it's probably an NPR. If you're getting a cup, it's probably NCR. What do we mean by that? If you think back to your problems, any problem that was a permutation, if you were getting ice cream, it was like getting scoops that were stacked, right? It mattered. The order of the scoops mattered. When you were doing problems that were combinations, they were like ice cream problems where you took the scoops and you just put them in a bowl and it didn't matter in any particular order. So that's just one way to think about it. You don't have to think about it. If it doesn't resonate with you, it doesn't really matter. Find something that will help you remember. Maybe just knowing that, hey, order matters. If I see a ranking, I'm dealing with permutations. And then if I don't, then I'm dealing with combinations. Now, we are going to take all these concepts and we are going to wrap them into probabilities. So the probability of some event occurring, this is what we did on our last section, is equal to the number of ways that the event can occur. So the number, and I just call it n, it doesn't matter. You could say, I could even erase this and write it out, just like I did the last class, and say the number of ways the event can happen, right, over the total ways that can occur, or not that event, but any kind of specific thing related to that event in terms of all your options. All of your options, all of your total options, all of the options for that specific event occurring, okay? So we're gonna see how these all tie together. We're gonna connect all these ideas. Let's take a look at the first problem, which is going to walk you through all of this, okay? So this first problem basically takes you through all of the steps to learn how to do a problem that combines permutations, combinations, fundamental counting principle with probability. Okay, let's take a look here. So I'm going to read the problem here. It says Kim, Katrina, Tyrone, and Simone have all been invited to a dinner party. They arrive randomly, and each person arrives at a different time. In how many ways can they arrive? In how many ways can Kim arrive first and Simone last? Find the probability that Kim will arrive first and Simone last. This seems like a lot of questions. I want you to take a moment here, and let's come back to the very first introductory statement. Okay? Kim, Katrina, Tyrone, and Simone have all been invited to a dinner party. They arrive randomly, and each person arrives at a different time. What does this sound like? This sounds like our problem where we were lining up bands, wasn't it? Band lineups, or comic lineups, or somebody is going to come here, then here, then here, then here, or somebody insists to go here, and then we have to do the rest. This is all the way back in permutations, isn't it? This is all the way back at the very beginning of section 11.2. So, in 11.2, what they would ask 11.2 is in how many ways can they arrive. Isn't that true? In 11.2, they would tell you this, and they would ask you, how many possible ways can these 4 people arrive? And what would you do? Well, you would come over here and you would say, let's see here, maybe I can do it, set up my spacing. Let's do it like this. So we would do what? Here's 4 positions, right? This is 11.2. How many options do we have for our first position? The first person arriving? Not 1, but how many? 4, right? 4 possible ways that the first person can arrive. All 4 of these people are options for step 1, or person 1. Then what? 3, then 2, then. Good. And then what do we do with these numbers to go and figure out how many total possible ways they can arrive? What do we do with them? Multiply them. Somebody got an answer? I'm going to need you guys to give me your numbers here because, what was it? 24. So throughout today's class, I need you to make sure that you give me the numbers because there's a lot of numbers that I can't crank out. 1, because I don't have my calculator because it's recording, and 2, because I'll need to make sure that you guys have the numbers that we're working on. So there it is, 24. There are 24 ways that they can arrive. Okay, now, part B. In how many ways can Kim arrive first and Simone last? So take a look. If you're linking this back, this right here is going to be the denominator. Isn't that true? The total ways that people can arrive. But now we have a very specific event. A very specific event. What is the event that they're trying to find the probability for? The ways Kim can arrive first and Simone last. So if Kim arrives first, how many options do we have for 1? 1. If Simone arrives last, how many options do we have for 4? 1. Those spots are taken. They're predetermined. Does that make sense? Which is very different from this, isn't it? This one tells you all the possible ways. What we're doing here is finding the ways that Kim can arrive first and Simone last. If 2 people are already taken out of the pool of arrivals, how many go in position 2? Yeah, 2, right? Because you have 4 total people, 2 are taken out. That means 2 people could potentially arrive. Namely, who are the other 2 people? Whoever they were. And then once one of them arrives, what's left here? 1. Answer to that? Just 2. And so that goes in the numerator because it's the number of ways that the actual event can occur. And now the probability that Kim arrives first and Simone arrives last is 2 out of 24 or 1/12. And that's how you do it. Does that make sense, everybody?
Why isn't 3 2 as well?
No.
The answer is just the whole number.
Wait, what?
Number 2, you put in fraction.
Yeah. 2 over 24?
They just asked for the answer.
No. I went all the way through it.
Oh. Okay.
Yeah, I went all the way through. So, yeah, so part B, in how many ways can Kim arrive first and Simone last? There it is, there's 2, right? But now, I just kind of tied it all together, right?
Okay.
It can't possibly be 2. Because there are 2 options for position 2. When one of the people arrive, now you're down to 1. That's like saying there's 4, 4, 4, and 4 here. That's not true, right? That's not the way you would run NPR, is it? You would go, you have 4 options here, 1 person goes, now you're down to 3, 2, and 1. Come back to 11.2. That's a big mistake if you put 2 again here. Okay? Cannot do that. All right, so there it is. So now you can actually answer the question in how many ways. That's 1 out of 12, and you're done. That's your probability. Does that make sense? Okay? This is sort of tricky, and it's going to take a while to go through just these 13 problems because you have to do a little bit of thinking through it. good. Okay, so now you have your first problem done. Step one in a problem is ask yourself, how many possible ways can things play out? Step number two, find out all the possible ways that your specific situation can play out. And then step number three, figure out the probability. In other words, here it is, total ways, specific ways, and then you can connect them. Does that make sense? Questions about that at all? All right, here we go. 6 stand-up comics, A, B, C, D, E, and F, are to perform on a single evening at a comedy club. The order of performance is determined by random selection. Find the probability that, before we even step into here, there's something we need to do first. There's something we need to do first before we even get started, and that is to figure out what. We don't need to even look at any of this. We have enough information here to do what part? 1, 2, or 3? 1, exactly. We have enough information to figure out the denominator of our probability of an event. Because we know how many people are performing. There are 6 people. So therefore, we can do step 1 here, which is to figure out how many possible ways 6 comics can perform. Isn't that true? So how many are there? 6, then 5, then 4, then 3, then 2, then 1. How many possible ways are there? 6 factorial, which is what? What is it? 720. Good job. All right, so we have the denominator for all of our answers here. So all of these questions, you will already have the denominator. So now let's go look at part A. Find the probability that comic F will perform last. Okay, so part A, comic F will perform last. So if you do your lineup here, what does that tell us about one of the positions? One's taken. Which one is taken?
The last one.
The last one, position 6. If position 6 is taken, and that's all they say, comic F will perform last, how many do we have for 1? 5. Then 2, and 1. What am I finding out right here? What is this going to tell me when I multiply all these together? Say that again? Your numerator. That is telling us not the probability, it's telling us the number, exact number of ways that comic F, one of the comics, will perform last, or the number of lineups we can get when comic F performs last. What is that?
120.
120. Now, is that the probability, 120? No. The probability is, for comic F last, is 120 over 720, which is what? 1/6, exactly. And there it is. Okay, there it is. Now, let's go to part B. Comic D will perform second, and comic A will perform first. So first, what do you need to figure out? Before you can even do the probability, what do you have to figure out? Come on. You have to figure out the numerator, exactly. The actual number of ways that that can happen. So, comic D is second, comic A is first. What does that tell us about positions 2 and 1 right here? They're both 1s. Very good. What does that tell us about position 3? 4. There you go. 2 people are out of our 6-person pool. That means you only have 4 to select from when you start with position 3. Positions 1 and 2 are already pre-filled. You start 4 and then you just go down. 3, 2, 1. And what do you get from that? Answer.
24.
24. Good. And so now, the probability of what? D second, A first. So D2, A1 is what? What's the fraction setup? 24 over 720. And now answer 1/30th. There you go. Nice job. Let's keep going. Part C. The comedians will perform in the following order. Do you even have to put anything down? What does that tell us? What does that tell us about our probability? It's going to be 1. Exactly. It's going to be 1. The fact that they tell us exactly what the order they want is for all 6 tells us that's one of the 720 ways that you can do it. You don't have to do anything. If you do your lineup, it would be a 1, 1, 1, 1, 1, and 1. F goes here, D goes here, A goes here, and so on. Multiply them all together, that's 1. But do you even really need to write that down? No. Because that is one very specific lineup. Does that make sense, guys? Okay? Very important you understand that. Now, let's take a look at part D. Very important to do this one because of the word or. Okay? So, the word or. It says comic B or comic E will perform 5th. Like we said before, the first thing you need to do, because you already know that the total number of ways that you can make lineups is 720, you have to find the number of ways this specific one can be made. So when they say comic B or E will perform 5th, what does that tell us about the 5th position? Is it just one option? It's 2. So this is 2 options here. Now, here's the tricky part. This tells us that there are 2 options for position 5. Are both of these guys going at the same time? No, they're not. That means that even though there are 2 positions or 2 options for 5, 2 options for 5, only one of them is going to get picked. If only one of them gets picked, what number starts 1? 5. A lot of people would put a 4 here, and that would not be correct. Because you have to understand that if you have 2 options for 5 and they're not both going, that means that after one of them is selected, you have 5 to choose from for position 1. Does that make sense? Then you just count down 4, 3, 2, 1, and that's okay to have that lineup. Okay? And so now, somebody tell me what this becomes?
240.
240, good. And so our probability of B or E in the 5th position would be 240 over 720. Anybody got the answer there? 1/3. Well done. And so there it is, 1/3. Again, this takes time. You know, we literally have only gone through 2 problems, but I hope you understand that. I'm going to recap real quick here before we go into the next one and look at this. When you read a problem, the very first thing you need to do is go find out your total number of ways that whatever can be done. Then read deeper into the problem and find out the number of ways that specific thing that they're looking for the probability can happen. Then divide the 2. That's it. Okay? You always need to be looking for that to occur. Alright? So here I'm going to erase this because you guys have a good example over there. Like this is a perfect example just to leave off to the side. Alright, so let's take a look at this. Okay, so don't read on to A through C. Let's just look at the beginning because what do we always need to do? Look for the total ways first, right guys? Okay, so here we go. A group consists of 7 men and 7 women. 3 people are selected to attend a conference. Stop right there. That's enough information to answer part 1. First, this looks very, very similar to something we've done before. Is it permutations or combinations? Combinations. There's no ranking. They're not picking a first, second, third, president, vice president, secretary, different positions. They're not doing that. What are they doing? They're just taking 3 people from a group of how many? 14. What's the setup since it's combinations? NCR, which is going to be specifically with the numbers 14C3. This, thank you. This will tell us exactly how many ways we can make groups of 3 out of 14 people. Does that make sense, guys? This is the general piece of information you need to start. Notice we haven't read anything yet deeper into the problem. We've simply found out the total number of ways we can make groups of 3 out of 14 people. Does that make sense? Okay. What was that again?
364.
364. Now, you guys now know how to do that on your calculator, right? Your NCR button. So that's nice. I'm not going to go and set it up. Okay. If you want to set it up, that's fine. But we know that 14C3 is 364. Now let's go do part 2. Okay. So what they do here is I'm going to skip over A and B. Okay, I'm going to just skip over. We'll come back to them. Okay, I just want to go straight to this statement first, and then jumping straight as if it's a real problem. Most problems are not going to walk you through A and B. Let's go here. Find the probability that the selected group will consist of all women. Well, if we just found out the total number of ways that we can get a group of 3, now we want to know the probability of a group of all women. We first then need to find out the number of ways to select only women. Isn't that true? Okay, so they're asking what's the probability of getting all female people on the trip? In order to answer that, we need to know how many ways can we make groups of only women? Is that combinations or permutations? Combinations. There's no order, right? It doesn't matter. Order doesn't matter, right? There's no ranking, okay? So, in order to do that, we back up. Look at B. In how many ways can 3 women be selected from the 7 women? And that's it. What's the NCR here? 7C3, exactly. There are 7 women. You're making groups of 3 for this trip, or whatever it is. Does that make sense, guys? Okay? Very, very hard to do, to see that. But we'll get more and more practice. So take a look here. Part A was this. How many ways can 3 people be selected from this group of 14? We just did that. It lines up with exactly what I've been talking with you guys about. Find the total ways first. 2, how many ways can 3 women be selected from 7? Why? Because you want a group of all females to go on this 3-person trip. And you only have 7 women to choose from. So you have to find out all the number of ways to get 3 women out of the 7 you have. Does that make sense? Okay. What's the answer for 7C3? 35? Okay. And so, we've now taken care of both A and B. We can go and do the probability. Which one goes on top? 35 over 364 on the bottom. And so, you know what I'm going to do is I'll just type these in one piece at a time. So, 364, then 35, then type a simplified fraction. Can we reduce that? I don't think so. So 35 over 364. Wait, what? Maybe you can reduce it. Maybe it's divisible by 7. It is divisible by 7. It's going to be 5 over
52.
52. Thank you. Great job. Fantastic. You guys are checked in. I like that. And there it is. Does that make sense? So every single time you do a problem, always find out your total options, then find out the specific scenario, then connect the two. Over and over again. Now, this problem with the transistors seems to throw students every time. So what I want to do is I want to actually do this one with the help me solve this, to show you, hey, this is not that big of a deal, and should you forget how to do it, you have a resource, okay? So let's read the problem, then we'll go to the help me solve this. A box contains 16 transistors, 4 of which are defective. If 4 are selected at random, find the probability that all are defective, none are defective. So this is a two-part problem. Does that make sense, everybody? Okay. So you can already kind of see the pieces. 4 things are selected at random. That would tell you your total weight, 16C4, right? Then how many are defective? Find that one. But if you don't see it yet, that's okay. Let's go through to help me solve this so that you can see that, hey, it's not a big deal, and they're doing it the same way. Okay, here we go. Let me zoom out for just a bit. And let me actually erase this. Okay? All right, so first consider the denominator of your probability fraction. That's exactly what they're saying. First consider the denominator of your probability, and that's trying to find out the total number of ways up to select 4 transistors out of 16. And that's what they say. Use the combinations, right? Combinations because order doesn't matter. You're just picking 4 random. Where n is the total group from which the 4 will be selected, and 4 is the R. So, with that said, what is the value of n, everybody? Yeah, when we're all done. But n is 16, right? And then R is 4, and so 16C4 is 1820. Now, let me back up so I can show you the same process. First, we got to figure out the total number of ways to select 4 transistors from 16. Isn't that true? You're selecting 4 out of the 16 transistors. We can't say which ones are defective or not defective. They all are lumped into the same group. So you first have to figure out all the possible ways you can select 4 from 16. And that's going to be 1820. Notice, same process as we've been doing over and over again. Okay? The next step is what? To find out the numerator. The number of ways of selecting specifically 4 defective transistors if there are only 4 defective transistors and all of them need to be picked. Now, what does that tell you? If there are only 4 that are defective and you need to select 4, what's our setup here? For C4, because the order doesn't matter, right? Okay? There are 4 defective transistors to select from, just like there were 7 women to select from. In the previous problem, you had 7 women to select from. You were taking 3 women at a time. This problem, you have 4 defective total transistors somewhere in that group. You're trying to get exactly 4 defective transistors. Does that make sense, guys? What is that? 1. In other words, the probability of getting all 4 to be defective is 1 out of 1820. Very hard to make happen. Does that make sense, guys? Okay, so there's only one way to do that. And so, what's the probability? 1 out of 1820. Does that make sense, guys? Okay, now let's move on to part B. Part B asks you, what's the probability of selecting none that are defective? Now, my question here is it the same total number of ways to get your answer?
Yes.
Yes, it is. So there are still only 1,820 ways to take 4 transistors out of the 16, or groups of 4. Now, instead of looking at the defective side, we're now trying to get all that are not defective. Does that make sense, everybody? So, let's come back here. 7 women, we're taking 3 at a time. 4 total defective, we're trying to get 4 out of it. How many in this group, if we know 4 are defective, and there are a total of 16, how many are not defective? 12. So we have 12 to choose from that are not defective. How many are we trying to take at a time? 4. Does that make sense, guys? I'm not going through this because I just don't want to keep typing through, but you get the idea. Does that make sense? But if you followed this, they would walk you through the same step. So you have 12. If you know 4 are defective, it tells you immediately that 12 are not out of the 16. You're still taking 4 transistors at a time, so that's how you set it up to find out the number of ways of getting 4 non-defective transistors out of 12. What is that? 495? And so the probability of getting 4 not defective is 495 over 1820. I definitely think that this can be reduced.
So about 5 is 99 over 364.
99 over 364. I don't know if we can go any further. I think that's it. Anyways, you guys get the idea, right? I hope so. This is actually a very difficult problem. Seems to throw students all the time. So, anyways, I want to close that out. That's it for that. In the event that you struggle in some way with it, just go to Help Me Solve This and walk it through. But now you know how to do it. For the defective part, find out first how many total ways you can select your number of transistors out of the total. Then find out how many are defective, how many groups are you pulling. Then put the 2 numbers together. Same thing for the non-defective. The non-defective is a little more tricky because after you get the same total number of ways, you got to pay attention to how many are defective to know how many are not defective. They don't tell you it's 12. So you just got to pay attention to that. Anyways, there you go. All right. So I'm going to move on. Here we go. Let's take a look at number 5 here. A city council consists of 5 Democrats and 8 Republicans. If a committee of 7 people is selected, stop right there. That is enough information to answer part 1, isn't it? That is enough information to answer part 1 in our problem. What is our setup for part 1? Careful, come back up. Is your problem different?
You have 5 Democrats, 8 Republicans.
Careful, guys. There you go. 13, C7.
Oh, total numbers.
Right, exactly. There you go. This is the total number of people you have to select from, right? This is the groups you are making, groups of 7. Does that make sense, guys? Very, very important. You recognize that. So easy to make a mistake there, isn't it? Okay? This, when we do 13C7, it will tell us the total number of ways we can make groups of 7 out of 13 people. Does that make sense, guys? All the unique ways we can do that. Anybody got an answer for that? 1760. Excellent. 1660.
No,
1716. All right. Thank you, guys. All right. Let's move on. Part 2 here. Let's keep reading. Find the probability of selecting 3 Democrats and 4 Republicans.
4 C3?
No.
Wait, that would be 7. Wait, 7 is 3.
It's a pair of things. You're going to need, here's my hint. You have two C situations being multiplied.
So I don't see three, so.
So five C3.
5C3.
And 8 C4.
Exactly, that's it right there. Take a moment, back up, remember back to, yes. Remember back to our combination section when you had how many come from this group and how many come from this group. You look at the Democrats, you have 5 Democrats to select from, you're taking 3 from there. You have 8 Republicans to select from, you're taking 4 from there. If you multiply them, you'll find out all the ways you can take 3 out of 5 and 4 out of 8. Does that make sense? 7 is what you see here when you're taking 3 and 4. See, that totals 7. Does that make sense, guys? Okay, very, very important, a little bit tricky. Answer?
700.
Is it 700?
Yes.
Okay, wonderful, very, very good. And so, now we can do the easier part, which is to connect them. Obviously, the probability of selecting what? 3 Democrats and 4 Republicans is going to be 700 out of 1716. That should be able to be reduced. Somebody give me an answer for that. Definitely reduced by, at least 2 to start. Can't be reduced by 7. What is it if you divide it by 2? 350.
350 over 858.
Divided by 8. 1. No, it can't be divided by 8. Is it divisible by 3? Somebody say that, divisible by 3?
It is divisible by 3.
Okay. So that's going to be what? 1,
No, never mind. 700 is divisible by 3.
but not 1716.
Yeah. Or 1716 is, but 700 is not.
You know what? Yeah, you're right. That's not divisible by 3. Let's just try 350 over 858 and see if that works. And it's not.
175, 429.
175.
Over 429.
Oh, it was divisible by 2 again.
Yeah.
Bad, bad. Yeah, it was totally divisible by 2 again. 429, yeah. Not paying attention. Not paying attention. All right, there you go. Good. So there it is. There's that one. Let's move on to the next problem. Okay, so you guys get the idea. Let's keep going here. Looking for too big of a number. That was good. Okay, so here we go. As men and women age, their risk of death increases. There are also health issues that can greatly impair older citizens' abilities to participate in activities and travel. Assume you are planning a 60th high school reunion and are wondering how many of the older adults would be able to attend if, here we go, you know that 18 women and 14 men are still alive and are told that exactly 10 of them will attend. Stop there. That is enough information to answer part, what? Part 1. Give me the setup. It's just like the Republican-Democrat problem from before.
32C10.
32C10, exactly. You have 32 people that you can select from, both men and women. You're taking 10 people at a time. There's your setup for how many possible ways you can make groups of 10 from 32 people. What's the answer?
645 12240.
Is that right? So 64,512,240? Okay, excellent. Now, let's go to the specific one. The exact number of ways you can make your event occur. And so remember, this is just like when you see 2 groups like this, you know you're dealing with like the Democrat-Republican type scenario that we just came from. What is the probability that you would have exactly 5 men and exactly 5 women? Okay, what are our setups?
18C5
18C5,
and
14C5. Doesn't matter what order you put them in, right? Women times the men, or men times the women. It doesn't make a difference. There's the men, the number of ways you can make groups of 5 from 14 men. Here's the women, the number of ways you can make groups of 5 from 18 women, just like Democrats, Republicans. Everybody got an answer?
171,531,36.
Okay, excellent. So 17,153,136, is that correct? Okay, so now we can answer the probability of selecting 5 men and 5 women for this event. That's going to be 17,153,136 out of 64,512,240. And the nice thing about this problem, we don't have to reduce it. It asks for 4 decimal places. So you don't have to reduce that fraction, just straight up divide it. Somebody give me an answer for that. Round to 4 decimal places. Should be point something. Is it still recording?
2659.
265.2659.
Yeah.
There you go. Does that make sense, everybody? Done. Really, really good. Nicely done. Okay, I'm going to skip number 7. It's not a big deal. Now let's take a look at number 8. This is also, just like the transistors, a problem that sometimes throws people off. So what I'm going to do is help you walk through it using Help Me Solve This. In the event that you forget how to do this, you can go, oh yeah, I remember doing Help Me Solve This. Okay, so let's take a look. In one lottery, a player wins the jackpot by matching all 5 numbers drawn from white balls, 1 through 42, and matching the number on the gold ball, 1 through 33. What is the probability of winning the jackpot? Okay, so this is going to be done again very similarly to what we've been doing over and over and over again in the previous problems. But this is a scenario that sometimes throws students off. So let's go take a look at how you might solve this. All right, let's take a look. To find the probability of winning the jackpot, both the total number of possibilities must be found, as well as the number of ways the event of winning can occur. Isn't that what we've been saying over and over again? Over and over again. Okay, fine, done, got that. Next, is this combination or permutations? It's combinations, because the order in which the balls come out don't matter when it comes to winning the lottery. Does that make sense, guys? Okay, so the order of them, like as if the winning lottery ticket is 54624, you could get 42456. Doesn't matter. I don't know if I got those numbers right, but there you go. So this is a combinations problem. Okay, the first thing you need to do is determine how many ways 5 numbers from 1 through 42 can be chosen. In other words, what are we trying to figure out? Let me erase this one. That way we have some clean board here. So we need to figure out step 1, how many ways 5 balls, white balls, right? Because we're dealing with the white ones right now. Everybody agree? 5 can be selected from 42, okay? And so obviously your N is 42, we're used to that. Obviously your R is 5, and so the answer, anybody got 42C5 of what that is?
850668.
850668, good job. Okay, there are 850,668 ways that 5 balls can be selected from 42 that are available, okay? So, now, how many different ways are there to choose the gold ball? How many different ways are there to choose the gold ball? There are 33, right? But how many are you taking at a time? 1. So there are what? 33. I mean, you didn't have to do 33C1, right? Because you're only taking one gold ball at a time. There are only 33 ways to pull that gold ball. Does that make sense, guys? But let's say you did it. It would be 33 possible gold balls. You're taking one at a time. So it's 33. Does that make sense, guys? Okay? Because you have to find out all the ways to select the white ones and the gold ones. And so, therefore, the total possible number of ways to select the white and the gold is by multiplying these two. Does that make sense, guys? And that's what they tell you right there. Somebody got an answer? 280-720-44. Is that correct? So there are 28,072,044 ways to select a white ball and a gold ball where there are 5 whites and 1 golds. Does that make sense, guys? All that is for part 1. Okay, so that's what you need to do. That's why I said a lot of students get tripped up here. That's why I wanted to show you the help me solve this. So 28072,044. Okay, good. Okay, and now, how many ways can the jackpot be won? Well, what do you have to do?
Find your denominator.
Well, we found the denominator. That's it right there. So now we're on to step 2. I should have left a little more space. Why don't I just come up here for step 2, shall we? How many ways can you win the jackpot? You have to get what right? Everything. So part 2 is just one. One. You have to get all the 5 white balls correct, and you have to get the 1 gold ball right. You have to literally land on the exact combination. Does that make sense, everybody? So to win the jackpot, you literally have to hit that exact one. So now we can do part 3, which is obviously what? Connecting these two, isn't it? So your probability of winning the lottery is what? 1 out of 28,072,040. And
It's 44.
44, sorry. There you go. Does that make sense, guys? And that's how you do that problem. Does that make sense, guys? Okay? Is it really that hard? No. The hard part is the white gold part, the denominator. Then step 2, there's only one way to win the lottery. And then the probability is 1 out of that, your one way out of your total ways. Does that make sense? But this is the tricky part for most people. Okay? All right, let's move on to number 9. So I'm going to skip this. Are we okay? Can I skip? This is the same problem. I'm just going to roll over because you have an example. All right, here we go. So let me zoom in just a bit more. Okay? All right, so let's erase this and let's keep going. Those were the hardest ones. The transistor one, the lottery one, always seem to throw students. That's why I like to do the help me solve this with it, and hopefully that helps you out in the event that you struggle with it. Okay, a hand consists of 4 cards from a well-shuffled deck of 52. Stop. We have enough information to answer part 1, don't we? What is it? 52C4, you got it. Because obviously you're trying to find hands of 4 cards at a time, right? You need to find out all the possible ways you can be dealt 4 cards, a hand of 4 cards out of 52. Somebody got an answer for that? 270,725. And sure enough, this is a problem where they actually walk you through it, right? Find the total possible hands, so we'll just walk through it with them, okay? Okay? Part B. A heart flush is a 4-card hand consisting of all heart cards. Find the number of possible heart flushes. Sure enough, they're setting up step 2, aren't they? The number of ways to get a heart flush. Well, let's see here. A heart flush is a 4-card hand consisting of all heart cards. What do you first have to know? Not P though. It's not P, because the order in which you get the heart cards doesn't matter.
So it's not saying because the order of the deck is just.
No, you don't have to worry about that. So, but remember to ask yourself, how many heart cards do we have to select from? 13. C4, there you go, that's better. So, you only have 13 heart cards to select from, right everybody? And you're taking 4 out of the time, so it's 13 C4. Pay close attention to that. That can be tricky. Answer? 7, 15. Good. And so obviously, part 3, the probability part of it, there's 715. Probability part of it is 715. The probability of a heart flush is 715 over 270,725. And nice, awesome. We don't have to reduce that. Round to 6 decimal places. Somebody got an answer, point something.
0.002641.
Excellent. Does that make sense? In other words, very, very slim chances. If you move that decimal place 2 to the right, you have 0.26% chance of getting that. Very slim. Okay? Let's do this next one. Let's see if you can do this one all by yourself. It's just like what we just came from, so I'm going to leave this here. Okay? Let's see if you can get the right answer. Here we go. If you are dealt 4 cards from a shuffle deck of 52, stop. Do we already know step 1? What's the answer for that?
So 2707.
Exactly. It's exactly what we just got.
The answer's the same.
The answer is the same. So 4 cards from 52, done. Find the probability that all 4 cards are diamonds. Is this any different from what we just did? No. Are there still 13 cards that are diamonds in the deck?
Yeah.
Are we still selecting 4? Yeah. So the answer is exactly the same as what we just got. Does that make sense, everybody? Okay, so I'm not going to keep going. All right, now let's do this one together, okay? So I'm going to erase this, okay? Oh, I can do that. Good. If you are dealt 3 cards from a shuffled deck of 52 cards, stop right there. What's our setup, everybody? 52, C3. Answer?
22100.
00.
Yes.
Oh, that's it. That's right, because it's groups of 3. Thinking it should be bigger. Let me erase this. 22,100. Okay, wonderful. Find the probability of getting 1 queen and 2 kings. 1 queen and 2 kings. Remember, you're taking groups of 3, so that makes sense. 1 queen and 2 kings makes 3 cards, right? This is like, here's my hint for you. This is like Republicans and Democrats. This is like men and women.
52C1 and then times 52C2.
You're almost there, but you don't have 52 queens and 52 kings to select from.
Oh, so it'd be 4C1, 4C2.
Yes, there you go. 4C1 times 4C2. Isn't that right? You have 4 queens in a deck, you want 1 of them. You have 4 kings in a deck, you want 2 of them. How many possible ways can that happen?
24 out of 2, 2, 1, 2.
Exactly. So the probability of getting 1 queen and 2 kings is 24 out of 22,100. And nice, they asked for decimals. I like that. That always makes life easier. Point what?
001086.
Or, yeah, there we go. Good. Very, very slim. Does that make sense, everybody? Okay. I'm going to let you do 13 all by yourself. Okay, when in doubt, use help me solve this. Okay, that's it. 11.5 is done.